In principle, this is not that's what would be this sum? Do you know this sum? Have you been to college ever? You have been to college?
1 minus
1 minus x to the n plus 1.
divided by
Now the case is that why these both results follow from this expression. Why these both results?
Apply the limit in.
Okay. So now in the
If the limit tends to infinity, so if x is less than 1 and between 0 and 1, so the x power n plus 1 is going to die out, it will be 0. So you get your divergence sum, convergence sum. And if x is bigger than 1, so x power n plus 1 is going to slow down.
that we have proven previously that if you for example take the limit n approaches to infinity, okay, what's going to happen? And this number is between 0 and 1, so this is going to be 0. Okay? And if x is bigger than 1, this is going to diverge out to plus infinity. Okay? And hence the whole expression is going to diverge. And hence the series is going to diverge. So that's one way to do it. How about if I want to think about this from the perspective of comparison test? Is it possible to deduce it through comparison test? Maybe a fun point to reflect. Okay. Okay. So now we have this test, and you can see that you can prove it without using comparison test. And we can use it to basically, we can prove it also using the comparison test. Have you seen this test? So suppose you have an increasing sequence of numbers. A1, A2, A3, so on and so forth. Decreasing sum, all non-negative. All non-negative. Then this series and we got one infinity an advantage from if this series converges. This k equal to 0 infinity 2 to the k times the 2 to the kth term of kk. Kn. In other words, you have this actually a1 plus 2a2 plus 4a8 plus 4a4 8a8 and so on and so forth. So what does this result says? That imagine I have a decreasing sequence. Again, as I said there, as you don't have a unified way to prove for sure a kind of a hard and fast rule, prove for sure that whether a sequence converges or not. So you have to think about using different results and tricks. And so similarly, you don't have a kind of a full time, okay, way through which you can apply everywhere and know that whether some sequences converge or not. So we are proving all these tests that when you want to check something, okay, to come to some series to basically to know that whether it converges or not. So you have all these candidates. So you can apply some suitable way. Okay. Try these ways to basically merge your convergence. So some of these ways. Obviously there are more, but so here you go. Okay. Read that theorem again that I told you about, which was talking about boundedness. Read the statement of that theorem. Think that whether this theorem can help us here or not. Obviously, you can't deduce it directly from there, but it gives you something very interesting. Theorem is giving you something interesting. So that theorem was saying, which is Newton's 3.24, the theorem is saying that if you have a series in which all terms are non-negative, then it is going to converge if and only if the sequence of partial sums is bounded actually. And here you have also something. So you have non-negative series decreasing additionally is given to us. And we want to have this series to converge actually. So what I can show that this series must have what? If the partial sums of this sequence, partial sums of the sequence is partial sums of
Sequence of what?
sequence of the partial sum from this series is bounded. So we just prove that that is bounded. So done. So I can apply that previous result to the values. There is no need that you just do it if and only. Use previous result to use it. Okay. Okay. So by that theorem, it is sufficient to prove that this guy, but the sequence of partial sums from this guy is bounded. Okay. Let's take it. So consider this as n, which is the sequence of partial sums of an, and I'm taking just like it's sum from n equal to maybe k equal to 1 to n, ak, and I have en, which is the sequence of partial sums of which is going to be k equal to 1 to n, and the k and what? The k. Or if I write it more explicitly, it would be better. Okay, so that you can see that what's going on. We'll make sense of it, but let me write this more explicitly. So the key Tn is a1 plus 2a2 4a4 plus 2 to the n and a. Agreed? Okay. So the trick that he is considering here, that you define this for basically A, so it's like A1 plus A2 plus AK. If this should be K, then we can have 2 to the K and A to the K, because I want to use N for something else. I'm already utilizing N. I need to use another symbol which should get basically deal with. So here is the U. So imagine the case when N is just like you take N something before 2 to the K. Okay, so I'm taking N something before 2 to the K. So my claim is that this N, so just give me a, if I compare these two in their current form, which one is bigger? The second one is bigger. So consider this, that whether you are convinced with this or not. So consider this, A1 plus A2 plus A3 plus so on and so forth plus A2 to the K plus 1 to the A to K plus so on and so forth, A2 to the K plus 1 and minus 1. More explanation. Plus A2 to the K plus so on and so forth plus A2 to the K plus 1 and then minus 1 from this number. Can you make sense of this series that what's going on? So I'm saying that A1, so the sum begins from, so like A2 plus A3. So the next is going to be what? So it's going to begin from A4, okay, and it will go to what?
A6.
6.
4, 5, 6.
So it's like 4 is what? It's 2 to the square actually. So it will go to the 2 plus 1 minus 1, so it's going to go to 7 actually. It's like it's going to start from 2. It's going to, so it's like 4 to 7.
Yes.
And then you take 8 and it will go to the 15 actually. So it's like 2 to the 3. So from 2 to the 3 to the
2 to the power 4 minus
so
1.
to the power 4 minus 1 actually. So just going to be 15. Okay? So are you convinced that this is going to be bigger than or equal to certain unit? If N is less than 2 to the
If it can,
huh?
if it can.
This is this. So it's like a sum from 1 to N. Then my Sn cannot go beyond this number. So think about that, whether it is
Combination.
Yes, it will go up to N actually. So on one side I have A1 plus A2 plus AN, and on other side I have all these terms. So let me give you one thing. What is the first term here? A1. And what is the first term here? So do you agree that this second term is going to dominate this second term? Yes. Because you have an additional thing. And the third bracket here is going to dominate the third term here. So in that way you can show actually that each bracket here is bigger than basically what this term is the number, and hence we can say that we have. Yeah, this should be true. Okay? But don't take this as on my words actually. When you re-practice it again, when you re-explore it again, just check it out for some K's and actually. Just check it out for some time that we can have. if this is the case, and what is this guy at? Isn't that? Let me write it here. Not go anywhere else. So once we prove this result, we're going to prove a very interesting result. Okay? Based on this. So payoff is going to be good. If Fn is less than or equal to, can I say that this is same as A1 plus 2A2? Because A3 can be dominated by A2. Plus
4
this is going to be 4A4. Okay. And so on and so forth, and plus the last term is going to be, so it's going to be
2k
about
k
K and which is T is equal to less than or equal to what? Okay. Now, why this conclusion is interesting? Why this conclusion is interesting?
सर के बराबर है Sn is less than or equal to
Sn is less than or equal to.
अच्छा
Because Sn is less than or equal to Tk. Why this is an interesting conclusion? Bounded by Tk. Okay.
सर व्हाट डबल एफ है ना सर हमारे पास, तो आपने क्या अज्यूम किया है अभी, आपने क्या अज्यूम किया है अभी कि एन कन्वर्स कर रही है या
We are saying that, okay, let me prove another identity and see these two identities both at the same time, and then see that whether we can conclude this result from the two identities that I have. So keep this identity in your mind. Okay. So that is the case when n is smaller than 2. So you can have other case if n is bigger than 2. Okay. If this is the case, what would be the relationship between Sn and
GT
So Sn is bigger than or equal to A1. I know it's been boring, okay, but it makes sense of it. Okay. At least I need to convince you what I'm doing. So these kind of proofs are not kind of proofs that you can directly deduce from previous fact. So you need to make constructions. So what we are doing is making small constructions. Constructive proofs are always funny. Plus 1 plus 1 plus A. So keep in view what is Sn? Sn is so it's like sum from A1 from up to An, and keep in view that n is bigger than 2k. So this is the index bigger than 2k. Okay. And on the other side, what we have A1 plus A2 plus A3 plus A4. So what do you think that what is going to be the next thing? So I can keep this track in our head. So 2 power k plus 1, so it's going to be from there. So we have to start from there. So it's going to start from 5 and we'll go up to what?
7 5 6 8
So it's going to up to 8 actually.
8
Okay. 2 bits. So it's like 5 plus 6 plus 7 plus 8, and then is going to be
From 9
9,
to 16.
9 to 16, and so on and so forth. And the last term is this. So last term is this. So my claim is that Sn must be bigger than or equal to this. Why this should be the case?
2 power k minus 1 होगा
Obviously 2 power k. So the n is bigger than 2 power k. So in other words, these
but you
terms.
want above than 2 power k. 2 power k plus 1 you have written.
They are given.
2 power k plus 1.
Sorry.
Sorry. Minus 1.
Now it is up.
So it will obviously be bigger than
This.
because the Sn is going to be bigger than that. Because this index ends at 2 to the k and n is bigger than that. So obviously Sn is going to contain more terms than this term.
And
So here's the point actually. If our given sequence is a decreasing sequence, then this should be true. That the first term is bigger than or equal to 1 over 2 k1 plus b2 plus a4 plus after plus 2 to the k minus 1 and a to z. Right, that should be okay.
sir, if you could take some how Sn is greater than this expression, sir. How Sn is greater than this.
Because let's just imagine I say that k is 3, okay? And n is bigger than 2 to the 3, 8. So it's like 9 or 10 or whatever.
Yes, sir.
So this sum is ending at 2 to the k. So it's like stopping at 8
Yes.
and the n is 9 again. So obviously
That is
there
clear.
must be some additional term. The next observation is this. Do you think that it should be okay?
Yes.
Okay.
Okay, that if you multiply by 2 this term, then we get y dk. What are you multiply by 2?
No, but like, what is the justification of this? Why this is true? Why do you think that? If you compare them term by term, you see that basically the above term is dominating. So like this term is bigger than this term. Okay, this is equal. This term is bigger than this term. Because A3 is bigger than A4, so obviously it's going to be bigger than A4 plus A4. So like this sum is dominating. So it's like this sum is dominating this sum term by term. Now, what does this guy is actually? So this guy is equal to 1 over 2 p. Why these two inequalities are interesting? They are sufficient to prove this thing. Think about it. Which partial sums? Sums of A and R. Okay.
And the terms are positive.
Okay.
So by the theorem, the partial sums are bounded and then equal.
Partial sums are bounded. And
So it's from series.
which inequality is following basically allows you to get into this inequality?
Equal number.
TK is also a partial sum. Just like we are saying, here we are saying that the partial sums of AN are less than or equal to the partial sums of okay. And here you are saying that the partial sums of AN are bigger than or equal to the partial sums of AN. So my point is this, that how this result is going to follow. Imagine this is bounded. So it's like this is convergent actually. So if this is convergent, what does it give you? Sum of the partial sums is going to be convergent and hence bounded. What if it is bounded? Then,
1 over 2 dk is bounded
okay.
and
So let me throw a pointer. So what I'm saying is that what does these two inequalities are showing? That either both series are going to converge or both series are going to diverge. Okay, can you see it from these basically? So either both are going to explode or both are going to converge. Now my point is this, okay? Straight from that perspective. My point is this, that from these two inequalities, it follows, which you have to dig out yourself. Okay? About it. For the seconds. That either the both A and this series is going to converge, okay, are both going to diverge. How does it follow?
is a bounded and one part is TK bounded.
So the conclusion is can you see a role of comparison test here? We are not just seeing it directly. We are seeing it in the light of the previous theorem, the three theorems, and the comparison test. State it clearly. We are saying that I have this series and this series. And I'm saying that if this converges, this must converge. And if this converges, this must converge. Okay? Have I written it? I should write it. Why have I said me write it? Both converge. Hope that I said it repeatedly.
Yes, sir.
So you have decreasing sequence and this sum. When I say that if this converges, then this series, okay, which is an interesting name. So what is its name at? Sometimes you call it able series. Able series. There are other names. These are that if this series converges, then able series converges. So in other words, what I want at the moment from you is that I would like to prove this result using these two inequalities and the comparison test and that bounded test result. Okay, so solve this statement for me. We are not going to move ahead.
So since let's say AN is convergent, then SN is convergent.
Okay.
And 2SN is TK is bounded by 2SN here from here. So with comparison test we can say TN is bounded,
Exactly.
and thus it would converge.
So how many people understood it? How many people? Now hasn't understood. Repeat it again.
Since AN is convergent, let's say assume AN is convergent.
This is convergent.
So SN is convergent. And
So the sequence of partial sums is going to converge of this series. Okay.
So
Okay.
we have in second inequality we have
We have this inequality.
2SN is bigger than TK.
Okay.
TK is sequence of partial sums. So by comparison test, you can say TK is convergent. Hence, that series is convergent.
So in other words, so since TK is smaller than or equal to 2SN, and this 2SN is converging. The SN is converging. Therefore, something which is smaller than that is going to also converge actually. Okay? So that is going to, therefore, if the series is represented by this is converging, then no, that's what they're saying by this is going to. Okay? How
Similarly,
about going backward?
dk is bigger than Sn.
Okay, then you have this again. So this is converging, then this must converge. It's right in front of you.